Okay, so I'm just going to start the Sallen Key low pass filter circuit drawing and the equations that go along with it. So first off, my name, the top of the page. Then I'm just going to start the circuit diagram here. So start off with the op amp in the middle, have that positive, have that negative, positive and negative up here. Have the wires coming out with the different areas, so we know which one's which. Then we'll start off with the voltage source down here, positive and negative. And we'll have the first one leading off into a resistor. That'll be our first resistor, resistor 1, which in our case is 100 ohms. That leads off into another resistor, which then leads into the positive terminal of the op amp. This resistor here is 27 kilo ohms. It's resistor 2. Okay. Then we connect up the capacitors. So the first capacitor is up here. And that goes back around to the output of the op amp. So that's capacitor 1. And in our case, it's 2.2 picofarads. And then our second op amp is connected at the end here. And goes back around there. And it's also grounded at this point. And this is our capacitor 2, which is equal to 3.3 nanofarads. That's much in there, but yeah. And then we have the negative terminal from the op amp, comes down and around and back into the output of the op amp. So this is our positive terminal here. So to power the entire op amp, bring this across, plug it into a voltage source here and another voltage source here. Yeah. So positive, negative, positive, negative, so that we have the positive going into the positive terminal, negative going to negative. Pop that into there. We also need a ground in between here. And yeah, so that's our circuit for our initial op amp. And then just the transfer function. So yeah, move on to the equations down here. So first off, transfer function. So we'll just go H in terms of S is equal to S squared divided by, so S squared plus S by 1 over R, or 2 C1, yeah, plus 1 over R2 C2. Then add that onto 1 over R1 C1 R2 C2. So that's our transfer function there. And then our frequency response for this circuit is going to be equal, H in terms of omega is equal to J omega squared all over J omega squared plus J omega times 1 over R2 C1 plus 1 over R2 C2 plus 1 over R1 C1 R2 C2. So as you can see, both these functions are basically the same. So we can say H in terms of S is equal to H in terms of W when S is equal to J omega. So yeah, and then we're just gonna have one more thing to do, which is differential equations. Try to fit it in the bottom here. So V out in terms of T is equal to Y omega times J omega squared plus A1 by Y omega times J omega plus A2 Y omega. And that's all equal to Y omega be 0. And then we can rewrite this in its differential form. So we can rewrite Y omega J omega squared as D squared Y in terms of dt squared. So in terms of time, plus A1 is then going to be equal to dy over dt plus A2 is equal to y in terms of time. And that's all going to be equal to B0 x in terms of time. So that's our differential equations summarized. And that's all the equations for the entire circuit for the transfer function, frequency response, and differential equations of the low-pass Sallen-Key filter.
Okay, so first place your op amp in the function. Then we take our first resistor, 100 ohm resistor, place it anywhere on the board. This will be where we put our input frequency, and we measure it across ground on this using the oscilloscope. We also want to place our ground inputs on the edge here, and we want to be able to put our ground into the op amp. I'm just going to place a wire in to power across the op amp, and then we place in a 27 kilo ohm resistor across a resistor here, and we place it into the first part of the op amp. And we also want to go across capacitor into the first part of the op amp, and then we take our other capacitor, place it in here, and then place it into ground, and that will create our circuit across the op amp. So this is the circuit here. As you can see, the input of the entire circuit is going to the resistor, which leads into the other resistor and the capacitor, and the resistor leads in to this capacitor here, and this all feeds into the op amp. The op amp is powered by this power supply here with 15 volts on each channel. So this is a grounding for the entire op amp, and this is powering it here. These two leads here are grounding the power supply, and this one here is grounding the entire circuit. Let's get there. Then this is the function generator, so this is supplying the input, which is applied across the resistor here, feeding into the entire circuit. And then we're using an oscilloscope to measure the function generator output. So on channel 1, this is measuring across the ground and the first resistor, and then this is measuring across ground and the op amp, and this is our two readings here. So this is the input and output of the circuit at a natural frequency. And as you can see, when we bring it down past the natural frequency at about 676 hertz, it begins to flatten out a bit more. And then when we bring it down even lower to around 274, 270 hertz, it begins to flatten entirely. And then when we bring it back up towards the natural frequency, it increases all the way back up, and then it starts to become smaller and smaller once we pass the natural frequency of the circuit. So we originally had an error in our circuit which caused the input to decrease as our frequency increased. So it caused it getting smaller, but we were able to fix this problem, and now we're able to keep the input at a constant.
So now I'm going to begin by drawing our circuit diagram in the LTSpice program. So first off, we're going to create a new schematic, and then we're going to add our first component, which is our op amp. Place that. Actually needs to be flipped around so the positive terminal's on the bottom. Perfect. Okay. So now that we've got that, start putting in our next component, which is our voltage source. So we have 3 voltage sources on this. One will be at the beginning, and then these 2 will be at the end. Next thing I want to add in is our 2 resistors. So first resistor there, next resistor here. Perfect. And then our 2 capacitors will be added in. So, oops. Added 2 by accident there. So I can just move this one up to where I was going to place the next one. Perfect. Let's move this across to make it neater and get this in line with the resistors. Perfect. So now that we have that, there's just one more thing that needs to be added into the circuit. Our 2 ground points, there and there. Perfect. Now we just need to wire up the entire circuit. So I will start by placing the voltage source positive line going into the resistor, resisting the other resistor, and then that going to the positive terminal of the op amp. So in between the 2 resistors, that's where you take out a wire and put it straight into the capacitor. And that will head down here and go into the output of the op amp. That will connect to the end there, and this will go into ground, the ground point here, and this will go into the negative terminal of the voltage source. The negative terminal of the op amp will come out and join the output. And then the last point we need is the positive terminal from the op amp that will power the op amp goes into the positive terminal of the 2 voltage sources here, while grounded in between the 2. So the negative come out here and go into the negative terminal of the voltage source. Okay, now that we have all wired up, we just need to start adding our values. So for the first resistor, 100 ohms. Second resistor, 27,000 ohms. Our first capacitor, this is going to be 2.2 picofarads. And our second capacitor is going to be 3.3 nanofarads. Our 2 voltage sources here will be 15 volts each. Don't need that. And now we're going to go in advance and create this into a pulse. So our values for this are 0, 0.5, 1. Then we want a small rise, so 0.0001. We don't really care about the fall. We're going to set this to 2, 4, and we only want 1 cycle. Perfect. So this looks like it's ready to run. So I'm just going to set the stop time for 3. And this should be good. We should be able to see a good rise here. Yeah. So as you can see, there's a nice step in our program here. Yeah, our circuit seems to be emitting the right output that we were looking for, this little step response here. Perfect. So we should be able to take this out of the program and bring it into MATLAB with and use it in there to get our B&A coefficients and be able to look at it actually in more detail than what we would be able to do in this. Okay, so now we're just going to take what we did in LT-Spice and move it into our MATLAB and actually get more accurate readings for our step response, bode, and our frequency response. So it's going to start off with a new script. So this is our script. So I'm just going to title it script 1, and I'm just going to put in our step response FS, frequency response, audio read, and then I'm just going to put in this file here. So V out wave, that's what we got from our LT-Spice. So that's our thing there. Let me just close the brackets there. And then we're just going to multiply it by 2 so that it shows the right values on the side, because we had to half it from LT-Spice so it would fit in our MATLAB, but now we're just going to multiply it by 2 to get the full range in so you can see everything. Times 2. Perfect. And then we're just going to get the length so we can see the entire length of the graph. So our length is going to be from 0 to the actual full length of the step response. Then -1, just to make sure we cut off the end because we don't want too much, divided by the frequency response. So then we're just going to plot it. So we're going to plot against our time against the step response. So it should give us a graph of our step response when we run it here. There we go. So you can't see it too clearly. We'll zoom in on this point here. Ooh. You can see our step response there, just like in our LT-Spice. Perfect. So now we're going to add to this just the X label, just to make sure we know what we're looking at. So that's our time in seconds, and our Y label is going to be our amplitude. I'll put a capital A to make it look nice. Perfect. So let's take one more look at our step response. Perfect. Let me just zoom in, if it lets me. No. There we go. So you can see our step response there. Perfect. And now we're just going to use our impulse response. So the response to the impulse is going to be like this, is equal to diff in the step response. Perfect. Comma there. So X is going to be to get the magnitudes of the FFT of the impulse response. This gives the magnitude of the impulse response. Perfect. And then FAX is just going to give us the length. So 0, length of X, capital X, -1, divided by the length x times fs, our frequency. And yeah, then we're just going to plot f(x) against x, and this should give us our impulse response. If it were run, yeah, just a bit of delay in there. There's our impulse response. It's on the 2 there, perfect. So yeah, looks about right. And now we're going to move on to our coefficients. So when we put it into the website, which gave us our A and B coefficients, it came out that B was 5101, 5202.53. So that's going to be our B coefficient, and our A coefficient is going to be equal to 1, 4562.29, 5101, 5202.53. Perfect. So that's our A and B coefficients, and now we're just going to get what they look like using sys1 tf. These are built-in functions in MATLAB. I actually wasn't able to get these on my computer, but I was able to use the online. So there's a second order function, so this is our transfer function for the two coefficients. And with this, we can actually show our step response, our Bode analysis, and our frequency response, again using the built-in functions. So our step response using our B and A coefficients is sys1. So this shows our step response here. Yep, looks about right. For our step response, looks just like our previous one, just a bit zoomed in and shows us where it's going to be leveling off. Then let's look at our Bode analysis for this, sys1. And yeah, looks just like our one that we got off the website with a little rise and then dip straight down. That shows our natural frequency limits and when it starts to go back down. And then just if we use H omega is equal to the frequency response using this built-in function of B comma A. Then if we just plot omega against the magnitude of H, this will give us our frequency response. Yeah. So now we can see it at 3 decibels and so on to the power of 10 to the 4. So 3 decibels should be along this line here. And yeah, that is our full MATLAB analysis of our values.